are going to do today is important. And I'm sure it will really benefit you. I really don't mind reading the just one of the persons here. Okay? It will be on record that we are the program. Okay? Because we all agree that we are going to be here. I don't have any challenge with that. Yeah, so I just want us to quickly revise the test and then we discuss one or two things. And the house is around 12 or so. Yeah, so for the test, which what really happened? You get to test it. What really happened? The performance was very good. I can't understand what happened because I was thinking that you were really holding for the game. But let us push through them. It says, use the following statement. This very attentive. Use the following statement to discuss the various types and/or levels of computer memory. Say, cost of memory unit depends on its access time. Cost of memory unit depends on its access time. The first you need to ask yourself is, what is access time? Alright? And then what are the types of memories that we're really talking about? Okay? And of course, you should be able from your discussion to differentiate them based on cost, okay, and what we're actually talking about, which is the access time. Access time, simply put, is what? Is the time taken to read or write to a memory, okay, or to a storage device, in this case now. Okay? Access time is what? The time taken to read or write, okay, to a memory device. Okay? So please take note of that. And then what we are saying that access time now is related to the cost of memory. What do we really mean? Now we are trying to say the faster it is for the CPU or whatever it is to access it, okay, the more the cost of such memory unit. Okay? For instance, if you look at your flash memory, okay, you have your main memory. Okay? Now, in terms of access time, okay, now anytime the computer, the CPU is looking for anything, okay, this is the first place it actually comes to. Alright, if it doesn't find it here, then it goes on to what? Main memory, and of course other types of memory. Okay, there we are. So we have sort of everything, call it primary, call them primary, call them secondary, call them tertiary, okay? So we can have them in the distance at least, okay? This will be offline types also, tapes and the rest of those things, okay? Now, access time, as we said, also means what? The time it takes to read or write to it. Okay? Now, the time it takes to read or write to that is what is in milli or microseconds. Compared to the time it takes to what? Read or write to main memory. In this case, RAM. Okay? And so we are saying, as you go down this way, okay, access time is what? Is for the decrease. Okay? Why what? Why cost, okay, is what? Increasing. Cost is going up as you come up, while access time is what? Reducing as you come down. That's basically what you're saying. That's basically what you are saying. And there's a reason for that. I think one or two of you got it. There's a reason for that. Okay? We talk of proximity. Proximity to the CPU. That is one of the major things that determines access time. The amount of time it takes to read or write to it. Okay? Cache memory, okay, is more or less what inside the CPU. I'm sure you must have seen one of the diagrams there. I think one. I don't want to show you something. Okay? Okay, this is good. Now, look at where your cache memory is. Alright? Look at where your main memory is. There is no way access time for this will not more than this. I mean, in terms of speed. There is no way. But this is the first point of call as far as CPU is concerned. Similarly, is what? As it's trying to write to it or read from it, okay, this is the first point of call. Before it is of coming to your what? Main memory. And we are saying, for that reason, this one costs more. Even though it's usually of a small size. Okay, it costs more, even more than your what? Main memory. So as you go down the lane again, okay, cost reduces, okay, capacity is also growing, but that's size now. Okay, so those are the things that we were expected to actually talk about. And the fact that proximity is what determines what access time. Okay, cache is the closest to memory, so it has a very good access time compared to the other types of memory that you have talked about. Okay, so at the same time, we can also expected to talk about cache memory, main memory, hard disk, and then maybe your that's like just a version of them. Okay, and then instead them in terms of what access time and cost. Okay, hard disk costs far less, okay, than cache memory. When you talk of cost per byte or cost per bit, okay, cost per bit of storage. Now get it. Okay, hard disk can be in the range of maybe let's say 500 GB now. Okay, and maybe this is sold, assuming, for 10,000 naira. Okay, RAM is maybe let's say 4 GB. Alright, and it's sold for like what? Let's say 5K. Okay, which one costs more? Okay, RAM costs more. Definitely. Okay, although this one is bigger. Okay, but RAM costs more. Do you get what I'm talking about? Okay, so this one is bigger, but RAM costs more. And RAM is what closer to your CPU. Of course, what that means is that access time for RAM is much better than the what hard disk. Okay, so I think that point is clear. Okay, for that first question. So it's really very straightforward. And don't take it for granted. Try to address it very well. When one or two of you actually mentioned the fact that it's based on proximity to the CPU, that's a major factor. Okay, that's one of the things that determines how much time it takes to read or write to the type of memory that we're talking about. Because yeah. I'm impressed by your performance. Given the time that you assume that I guess that I can do this well. Okay? Yeah. That's what I said. Rex here. Obina, Francis. You are told that. Okay. Those are the few ones that actually that is performed. Others did not too badly, but they are not up to 15, so it's not. I can't be distributing that one. The class rep. Sir, I did not do that one. Okay. So for those of them that are going to see them, to know them, some of them are not know them. Okay, so let's go. Yes, it says that this is also very better. Second person says, give the range of values. Please, I want you to just understand this. This is very simple. I'm sure when you saw the native questions, some just got confused. You know, it's not about that. These things are very, very simple. They are really very, very simple. Now, second question says, give the range of values, positive and negative, that a 16-bit register can store for each of sign magnitude, first one's complement and two's complement. Okay? For 16 bits. I was surprised the kind of magic that some people were doing. Sorry, please. Can you be lost in okay? The kind of magic. Some people just decided to break down the 16 bits into binary. I don't know what they are going to do with that. I don't know. And then they are just writing all manner of things. I don't know. But what he's saying is part of what you have made. It's part of what you have in your notes. Now, if you check your notes, and even if it's not there, it's what you need to know. Because you might not just get everything that you need from your notes. That's why you are 300 level students. Okay? Most of the things that you need to know now, you might need to know it by yourself. But that's when you can keep it better. Correct? Most of the things that you'll be taught now will just be like laying foundation. Open your eyes to see those things. And of course you can build on it. Okay, so don't expect to be giving just everything. And of course, some of them are meant to, just to obey a little, to see how far you have understood. Alright, so, yes, there's a logic because there are two things there. One, it says 16-bit register. Okay? 16-bit register. But what we are really looking out for here, okay, is not particularly about the register. No. Alright? If it's about just the register, then we'll be talking of the smallest value or the biggest value, just those two. Okay? And of course, when you pick 16 bits, what do you have? What should be the maximum? 16 bits, that's what? That's what? Is it 32? 16 bits should be 655. Yeah, 36. Okay? So, some will have simply said 0 to 655. That is what this can produce for you. Okay, 8 bits can go as far as what? 0 to what? 255. Okay? Now, this is good. This is good. Alright? Because by the time you get what you are looking for, it must sum up to something like this or sum up to something like this. For instance, let's start from a smaller unit. Let us start. Assuming this is not 16, assuming I put 4 here. Assuming I put 4. Now, 2 raised to the power 4 is what? 16. I'm sorry. 2 raised to the power 4 is 16. What this 16 stands for is 16 possible values. 16 possible values. Okay? That's what you can have for each of those representations with 4 bits. Get it now? 16 possible values. That's what you can have for each of those representations. Alright, so when I say 16, I'm trying to say you can have as many as 2 raised to the power 16 possible values for each of those representations. Get that now? Okay, so now if you look at your sign magnitude, look at it. Let's start with just 4 bits. Let's start with 4 bits. Okay. Now, 4 bit means what? 0, 0, 0, 0. Okay, that's for 0. Good. This is 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0. Okay? 0, 1, 0, 1. Then what? 0, 1, 1, 0. That's for them. Okay? Then that what? 0, 1, 1, 0. Good. Now, sorry. Now, that of course is still going on. So, now, what happens here? This one goes to what? 1, 0, 0, 0. This one is what? 1, 0, 0, 1. Now, this is for sign magnitude. Okay? This is for sign magnitude for 4 bits now. Okay? Is this 0? This is 0 now. This 1. Okay? This is number 2. Is that what? This is 3. This is 4. This is 5. This is 6. This is 7. What is this? What is this? Huh? This is what? Minus 0. It's not 8. I get it now. This is what? Minus 1. You understand? Huh? Sign magnitude. What is about sign magnitude? One of the bits represents the sign. Okay, either positive or 0, and then 1 for negative. Okay, and we have started. Okay, this is 0. Agreed. Okay, and of course, other must follow because of their signs. Okay, but as soon as you come here, you come here, it changes. Okay, it says what is the sign? Whatever is there is the magnitude. Sign here is negative. What you have here is what? 0. That is giving us what? Minus 0. Okay? Likewise, sign here is 1. Imply what? Negative. What do you have here? 1. Okay? This is also 1, 0, 1, 0. Okay? Implying what? Negative 2. Now, this is how this circle is going to go. Okay, let me just continue that here. This is 1, 0, 1. 1, 0, 1, 1. 1, 1, 0, 0. 1, 1, 0, 1. 1, 1, what? 1, 0. And then what? 1, 1, 1, 1. Good. Now, what is this value? Negative 3. Good. And what's this value? Negative 4. I get it now. Okay? And what's the value? Negative 5. This is what? Negative 6. This is what? Negative 7. Good. Now, how many values are here from 4 bits? 16. So this is what we are really we're looking for. These are the 16 possible values you can get with 4 bits, other words, sign magnitude. So, what does this rate now give us? This rate now gives us something like minus, okay, 2 raised power n minus 1, okay, plus 1 to what? Positive, of course, 2 raised power what? N minus 1 minus what? 1. Okay, so we can put any number of bits that you have been given to get what you want. I've just used 4, and it's giving me exactly this. Okay, this is what's giving me. Alright, so you have that there. Yes. No. Not going to be minus. Because if this one gives me 8, okay, check now, check here. If it's minus 1, okay, then it's going to be what? 8 minus 1, or minus 8 minus 1. That's going to be minus 9. That's what is in this range. But if it's this range, it's going to be minus 8 plus 1. And give me what? Minus 7. Minus 7. Okay, so it's going to be minus 7 to plus 7. Minus 7 to plus 7 plus what? The 2 zero values. The 2 zero values now. Positive 0, negative 0, as you can see there. Minus 7, good. Minus 7 to what? To plus 7. Minus 7 to plus 7. That's how many values now? This one. How many values are here? No. How many values are here? 14 values are here. Okay? Apart from what? The 2 zero values. Okay? So this is going to be 14 values, then plus my 2 zero values, giving me 16 values. Got that? Okay? So that is why it's this range. I think this one should be in your notes. Let's see that from the what do you call it? One's complement. Okay? Yes. Alright? As a general formula to use when you are giving anything of that nature. This is my target actually. Okay, but I need you to understand where this is coming from. That's why I discussed this. Okay, but this is my target. If you're able to know how this one has come from, I mean, anytime you are giving a number of bits, you just substitute it and get what you want. So that's the point. Okay, let's see. Prime Minister, what do you know is a prayer and it's in the it's prayer and she's doing that for you. Or by the time, sorry. Let's do it. Okay, so let's see for one's complement now. This is for sign values. This data of it. This is what to use. So, in place of 4 that I've used, just put what? 16 there. Okay? Or whatever range that you get, that's what the number of values you can that are possible. Yes. Yes. Just say this is the range of values and just put what? 16 there for me. This is going to be like what that? This is going to be like 6, 5, what? 6, 5 times 3 what? 3, 6, 8. Okay, 3, 7. 3, 6. No, this is very going to do that. This is going to be like 3 raised power 15. That's 3, 2, 7, 6, 7. Okay, up to 3, 2, 7, 6, 7. By the time you add both of them and the 2 values of 0, okay, you will have what? You will have 2 raised power 16 values. Okay? Let's do it. Now let's see that of 1's complement. Let's see that of 1's complement. Now, I'm going to erase this also for 4b, but I'm saying 1's complement. Alright. Now, that's for 4b now. This is 0, agree. This one, like that, okay? Up to 7, there's no problem. Is that what? There's no problem. Now, what happens when it comes here? What happens when it comes here? What is this value? Is it minus 0?
This one. 7.
Look at it very closely. What is this value in 1's complement?
7.
Eh?
7.
No, that's the minus number. Okay? Now, let's see. Now, what number? Okay, look at it very well. Look at this number and look at this. Compare these two numbers.
Minus 7.
So, definitely, this is telling you that this is a bitwise complement of this. And that's the 1's complement number. 1's complement is what? Bitwise. Once you interchange the bit, it gives you what? The negative of the positive. You get that now? So, this one, automatically from here is what? Minus 7. Are you getting it? That's it. Okay, this is 0, right? There's no problem with that. This is 1, this is 2, this is 3, up to 7. Alright? There's no problem with that. Now, how do you form minus 7 in 1's complement? How do you form minus 7 in 1's complement? Bitwise complement of what? Of positive 7. Good. And we have said this is positive 7. This is positive 7. So what is minus 7? It's just what? Making this one 1, making this one 1. 0. And that's what the next thing is giving us. Get the number. Okay, so that's why this is going to be what? Minus 7. Now, when you move down here again, check. This is going to be what? It's just what? Bitwise complement of 6. Bitwise complement of 6. So, that's going to be minus 6.
I'll stay here.
Right? Similarly, if you look at 5, alright, this is going to be what? Bitwise complement. So, this is minus 5. That's minus 5. This one too, it goes for what? Minus what now? Minus 4. Okay, that's very clear from there. Minus 4. This one goes for what? Minus 3. It's very clear there. Okay? Minus 3. And then this one goes for what? Minus 2. It's very clear there. Okay. Minus 2. And what about this one? Minus 1. Okay? Minus 1. And then, what is this value? So, this is what we get. Now, we have 16 values also for 1's complement for 4 bits. Okay? Now, let's now derive its general form, okay, from what you have done. Let's now do what? Derive its general form from what you have done. Alright? So, we can say here that we have what? We can put what is happening. Let me see. Okay, yeah, still the same thing. We have minus 2 raised to power n minus 1 minus 2 raised to power n minus 1 minus 1 minus 2 raised to the power n minus 1 minus 1 to, of course, positive 2 raised to the power n minus 1, okay, minus 1. Does this fit into what we have there? Does this fit into what we have there? So if this is 4 now, this becomes what?
N.
Huh?
Level of bit.
This becomes what?
Minus
9.
is it 4? It's 4.
What's that? Yes. Now,
Share
it's okay. Is it okay? Huh? It's different now. Okay, so if you say this is 8 now, 8 minus 1, that's 7. Giving you what? Minus 7. If you say this is 8, okay, giving you what? 7. So you have what? Minus 7, then up to what? Plus 7. And of course your two values for 0. Alright, so that also forms 16 values. That also forms 16 values. So we have that there. So I will not give you the general form for the two's complement. I will not go through this again. Alright, so that you will take note of it. Alright. This, have you written this? Have you done this? Yeah, let me see some of my people about it.
Shalla. Then let's check it.
Esther, that is, or maybe I know the name, but Laura, I got the moon. Okay. What do you ask for that? Rex. Okay, now. Let's do it. They forgot. Alright, let's go. So please take note of this for one's complement. For two's complement, it's simple. Two's complement is 2 raised to the power n minus 1. 2 raised to the power n minus 1 minus 2 raised to the power n minus 1 to 2 raised to the power n minus 1 minus 1. Two raised to the power n minus 1 to 2 raised to the power n minus 1 minus 1. Take note of them, please. Your voice. What's that?
Careful. Very good.
Okay, for this, right? Okay. Now, let's see for two's complement. You see, I should just see. I didn't want to actually go to that one. Now, there's no, I've already said it in this class, there's no problem representing positive numbers. Okay? The challenge comes anytime it involves what? Negative numbers. And the negative numbers usually recognized by a sign of 1, a bit of 1. Once the bit is 1, it implies what? A negative number. Alright, so please, let's see this. Now this is up to 7, also for 4 bits. Okay? This is 7. Now, when it comes to 8 here, what do you have? What do you have? Yes? What's this value? It's What's this value in two complement? This one now. Yes? What's this value in two complement? No. Now, what you should do is to get this value, okay? This is what you have. Alright? This is what you have. Alright? Take this value, do a bitwise complement, okay? Okay, and do what? I like one to it. Alright, let's see. What does it give us? This is 0, 0, 0, and 1. And 1. It has to be back there. It has to be back there. Okay. So, you have it there. You have it there. Because there is no 8. Okay, yeah. You have 8 there. 8 is there. 8 is there. Okay, 8 is there. So this is 8. This is 8. Okay, this is 8. Now let's pick this again and see. We have 1, 0, 0, 1. Okay. What's the bitwise complement of this? We have 0, 1, 1, 0. Add 1 to it. What's that? So this is what? 1, 1, 1, 0. Okay, so this number is 7. And then what happens is that this number is what? Minus 7. Okay? This is what we get here. So this is minus 7. Okay? Now, if you look at this, if you look at this, you have what? 0, 1, 0, 1 plus 1. What do you have there? You have 0, 1, 0 what? 1,
0.
This way. And then what? 0 giving us what? This is 6. Which means this must be what? Minus 6. Is that not? Okay, so you can put it that way and then you get very good. So you can. Sorry? What? Minus 1. Of course, because there is no minus 0 here. Now, in two complements, there is no two values of 0. 0 is 0. 0 is 0, 1, 0. Okay, yeah. Yes. Even me too, I'm hoping. Now, see. Let's see if you are really going to have minus 8. Alright, from what you are saying. Because if this is going to be 2 raised to power 3, okay? If this is going to be 2 raised to power 3, then this is going to give us minus 8. Minus 8 to what? To 7. Minus 8 to what? Positive 7. Minus 8 to positive 7. Minus 8 to what? Positive 7. That's what this is going to give us for what? 4 bits. Okay, so it will not be wrong to actually put minus 8 here. Okay? It's not wrong because that's the identity that we are going to have here. Alright, but after you have tried to be able to confirm that. Okay? So highest negative will be what? Minus 8. There will be minus 8. Okay, so I'm sure it's going to start from this point. Alright? It's going to start from that because positive and then additive of it is still giving us the same thing. Okay, so we can sufficiently this is it. Okay. Now, please take note of the formulas, okay? And let's move on to something else. Yeah. Who just came in now? Who just came in? You? Because I don't experience you. Yeah, question 3, Madam is to see me. So what value in both binary and decimal will be stored in an 8-bit register as the result of the following calculations. Alright, now most of you, or some of you rather, lost some maths because you decided to use calculation. Just extract it on now. Alright? And what we are expected to do all through is to generate your binary values. Generate what? The binary values. So if you have been given 147, okay, you have to show us how you got 147 in binary, not with the calculator. Yes?
There's a way that you can find it in binary, not using the division.
There's a way back? Okay.
Can you show you that?
Okay, of course, yeah. I noticed some of you, yeah, of course, I noticed that some of you maybe 16 times 2 like that, so some kind of arrangement. I'm trying to figure it out. Okay. The fact that if you have 1, 1, 1, 1, 1, okay, assuming, okay, this is for how many bits? 1, 2, 3, 4, 5, 6, 7, 8. This was what? 128. Okay. This was what? 64, 32, 16, 8, 4, 2, and what? 1. Yes, 0. There's no 0.
Everything would be
Okay, sorry. So whatever is here is just starting one. Of course, that's the one that's there. Okay, so that's one. Yeah. Okay, so now if you decide to go this way, that is still reasonable. Now just press the calculator and then put in it there. Alright? Of course, from there you'll be able to pick your 147. Now, maybe pick this one. Okay, join it with what? 16. So that's 144. Join it with 2. Join it with 1, and you have to be 147. That's the look. That's the look. Okay? So that's the look. But we are expected to show how you got it. That's the most important thing. And then, just as I was saying, if your result is 270, or rather 82, 282, that's what you got as the summation, okay, which of course is going to come in binary. Okay, this is supposed to come as binary addition of those two values. Okay? Well, I'm just writing this, I don't know. Alright? Whatever it is that they are going to get here, alright? Perhaps it's going to come with what? An overflow. Alright? It's going to come with what? An overflow. As it did actually. Now, most of you, or some of you, decided to kill this overflow and then add it again. That is usually what is done for one's complement. And we call that what? N around carry. Alright, but that's not what we are asked to do. That's not what we are asked to do. What is the result that's going to be stored for this? Using what? 8 bits. So all that you are supposed to do is just to pick your 8 bits, okay, from your least significant bit, not from your most. Some pick from the most and drop the least. That's all. Okay? Pick from your list, okay, and then it's going to have to drop the the most, which is an overflow. Okay? And whatever it is that you get, that's what's going to be stored in that register as the result. Okay, so I think for one it was 26, for the multiplication it was just 8. Okay, 8, which is very simple. Yes. Now, pick 8 bits, okay, that represents what you want to store, right? And say this value is also in decimal. That's why I say both in binary and decimal. Some stuff as binary, still back to okay, so we have that then. And then question 4 was quite straightforward. I will not spend time on that. Except that I gave you what would have made your work easy. But some of you did not follow that. Some of you didn't follow that. Alright? I said, please take note of this. I said, when there's no problem with the integer part, okay, you can easily get that one. For the 1.2, give what? 0.2 by 2, 0.4, give the 0.4 like that. So this we are going to continue anyway. This is 1 by 2, 0.8 by 2, 1.6, sort of coming back to the possible copy. Now 0.6 again by 2, 1.2, sort of coming back this way. Up to 10 bits. Up to what? 10 bits. Just 10 times and then stop. Okay? And the rest after that is what? 0. Yes?
I think it's very serious. This is how you calculate 2, 1, you first option this.
Yes, individually of course, and then do the binary addition. Everything should be done in binary. Everything is expected to be done what? In binary. That. Okay.
I see that one, the number because 64.
Yeah. Let me just answer one more question. Not everything.
Put the zeros.
Right? Nobody got underflow. What is that? Underflow. Overflow. Underflow. What's the difference? What's the difference? Underflow. Antonio. Underflow. Did you get it? You have not seen it. Yeah.
Underflow is the situation in which the bits to be placed inside register are less than the required amount. Like for instance, placing a square of 4 bits inside an 8-bit register.
That one is sufficient. That one is overfeeding. Now, somebody said underflow is just the opposite of overflow. Okay? And I quite agree with the person. Okay? It is actually because just as you have overflow, where it occurs in such a way that what you are trying to represent, okay, is too big for the space available. Is that not? Now, underflow is a value that is too small, okay, that is too small, okay, for the space provided for it to be stored. Now, yes. Too small in the sense that it's a negative value, not a positive value. Too small in the sense that what is a negative value, not a positive value. You get that now? For instance, try to store minus 120 minus 60 in 8 bits will not work. Get it now? Now, this of course is what? Minus what? 180. Okay? This one cannot be stored in what? 8 bits. You get that now? Okay? This cannot be stored in what? 8 bits. What is going to call for is what? Another flow. Now what is going to call for? Not what? An overflow. So there's a difference. Okay? Here you have a very small value that cannot be represented in the space provided. Okay? That becomes what? Another flow. Mostly negative values. Mostly what? Negative values. So that's the difference. You got that now? Okay? I got it. Did you write that?
Yes, I wrote the definition of I didn't get the example.
I didn't get it.
I wrote
Yes.
I found the definition.
So that. Yeah, it has to be a very small. In fact, usually that's what happens for very small floating point numbers. Very small floating point numbers. Numbers that maybe could be of exponents less than minus 1 to 7. Okay, that's really very small. Okay, and then you are trying to represent it maybe in a 16-bit or thereabout and made available. That will lead to another one. That's it. Yes, most of you got custom form, but you did not explain why. You have to explain why now. I don't say correct. For what? Why? How? How is it not correct? How now? Why?
So during the test, just tell you.
Okay, so it's not everything that you've been asking me during this now. Yes, no. So you must state why it is correct or wrong. Yes, now. Yes. So that's why when I thought penalize you so much, okay, for those that got it, I didn't explain, I only remove one mark. Just one, out of 5. Out of 5, so for lack of explanation. So that's not bad. Alright, and then of course the last one there, the last one is also very straightforward. I was trying to explain that in the last class. That one is really trying to walk back to a particular value. Please, are you with me? Actually got that. Is that what you have done over here? The last question section B on the C2661004. Now, listen to this. Listen to this one. This is C2661004. Hexadecimal. Okay? Now, you will still see this. I don't know when, but you will still see it. When you see it, what is expected of you, alright, to start working on this, is to expand this. And what do I mean by this? Like that. Okay? Each of them can be represented with 4 bits, 4 binary bits. Okay? So, for instance, this C now, I think it's 1. This C. Okay. And what? 0, 0, 1, 0. Okay, so that's what you do for all through. Alright? And when you get that, now place your formula, your sign, okay, exponent and your matrix. Because this is going to give you 32 bits. This is going to give you how many bits? 32 bits. Okay, so from here, there is your sign. From there, there is what? Exponent. How many bits is that? 8. And of course, this is going to be what? How many bits? 23. From which you can just pick just a fraction of that, not the entire 23 bits. Right, so we have this one as our sign, this one, telling you that this number is a negative number, first of all. I think the number should be maybe negative 32.5 or so. I can't remember. Okay. So now this one is alright, this is okay, that's 0, 1, 1, 0. Okay. Let me just pick this one. So this already wrong. I'm going to pick 1, 2, 3, 4, 5, 6, 7, and 8. Alright, for this E. That's 1, 0, 0, 0, 0, 1, 0, 0. Okay? That's for that E. Okay? Now, what is this value? Everything else is the what? Matrix. Okay? What is this value? Okay, simply put this is what? 128, right? Plus what? Plus 4. You just have to get it done now. Giving you what? 132. Now, how would you have gotten to this point? No, nobody would have added what? 1 to 7. So, they are interested in grouping what added to get to this point. Alright, and that's what? 5. So what you had initially was something of this nature. 1 point something times what? Series power 5. Yes. Yeah. Have you got that? I didn't what I said. Yeah, I said if you need to solve this, please let me just come again. Okay? Embrace it. I agree. Did you get this one? Somehow. I've not seen the script. Now, I said you need to first of all do what? Expand this. That's the first thing. And anyone that did that, I think got 1 mark or so, even if you didn't complete it. But that's the first step. Alright, that's a very first step. So we are trying to expand this, in terms of base 16. That's out of reach. The kind of number that they got. I don't think there's any computer that can store that kind of number. So really expand this, and that's what I'm trying to do here. C is 1100. 2 is 0010. Alright, 6 is 0110. Similarly, this one goes to the same thing. Okay, but I'll just stop here because I needed those values for this two. And I said my sign is 1, meaning that the value that I'm actually going to get is going to be negative. That's what it is. And I said the next thing that I need for this E is what? 8 bits. 8 bits. Okay? And then I count them 1, 2, 3, 4, 5, 6, 7, 8. That's what I will say. Are you with me? That's what I will say. And this amounts to what? 132 from our calculation. This is 132. Alright? You should know this one is 128. This is 128. This is 4. So this is 132. But if you are to do this from the other way, alright, 132 will have been what? Biased by 127. Okay? And that's how you are plotting 132. If you are working from Okay? Are you clear? Yes. What else? Apart from RAM. Now, the truth is that it's not all time alone that determines the speed of the computer or performance. However, RAM enhances the performance, okay? Because it makes it possible for more programs to run, okay, when it's available. Alright? Because at any point in time, every program that you are running is running on your RAM. You get it now? Okay? Now, hard disk does what we call permanent storage, okay, until you delete it. Okay? But every time you want to run like Microsoft Word, okay, PowerPoint or whatever, it must first be loaded into, onto the RAM. Alright? So if you have enough size of RAM, okay, that means what? More program can run. Alright? More program can run. And there will be less of what? Swapping, paging, pager. Okay, trying to get more of those programs to run. If there's enough space, a large part of any program can be run at any point in time. Okay? But some other ones actually also, as far as I'm concerned, RAM enhances what? Performance of the computer. But of course, the speed and the type of your CPU also matters. CPU by that I mean your processor. Okay? The speed of it, okay, also what matters. Alright? You know that your battery number on your test. You look part of it. What is 59? 59 what? 59 76. 76. It's missing. But of course I know you that's right. It's not missing here. Okay. So we have that here. And just as you know, memory forms a major part of the computer. And when we talk about memory, it's not just, in fact, some call your computer memory RAM. Okay? But when we talk in this context about memory, we are not just talking of RAM. It's get a topic of mind. We are talking about everything that can be used to store and retrieve. Alright, so we also talk of your registers, talk of your cache memories, okay? Okay, all of them are what are storage devices. Say, although a computer memory is simply in concept, it has been that wide range of type, technology, organization, performance, and cost. You have this note. There are so many things we can say about your computer. About your memory. Alright? Maybe with Dr. Zeta, you may go into some more details of memory. Okay? It's been segmented now. It can't be. In fact, I'm not part of this course. Yeah. I'm only standing in for. Yeah, I'm only standing for it. So, once I get done with my part, you'll not see me again. Exactly. So we have that there. Okay, now, as you are aware, memory of a computer computer is in levels. Okay? Memory of the computer is in levels. And that's a part of the question that I asked. You know, and we have various levels. And that's when you can talk of primary memory, secondary memory, tertiary, and all of that. And then now we talk about levels in terms of proximity to the CPU. Okay? Because as far as the computer is concerned, there is nothing else that makes use of memory content like your CPU. Okay? That's where the central processing unit. So everything, okay, revolves around, you know, what happens there. And that's why the levels are actually based on what? Proximity to the CPU. As you move away from the CPU, there's a level. Inside the CPU, there's a level. When I talk of your cache memory, outside it, there's your main memory. And outside that, there's your hard disk, okay, and some other ones that follow, okay. Some other ones require controllers, like maybe your tape drives like this, okay. Those ones are further more from your CPU, and they form their own level as well. You have that there. See the registrar, cache, and the rest of that. Right, and we can actually talk about memory based on what you can see here. Based on what? On location, on capacity, unit of transfer, access method, performance, physical type, physical characteristics, and of course organization. We can talk about them in a number of ways. We have just picked some of these things, and then that's what this note is actually about. Alright, so just one of them has to do with location. Okay? Now we say inside your CPU, you have what? Registers. What are registers? What uses registers? Right. Now, okay, yeah. You are still
Alright. So it's okay now.
okay. Now, let me go back to one of the slides. Let me go back to some. Yeah. I'm going back. Go back. Yeah. Now, I want you to look at this diagram. I want you to look at this diagram. What do you think these two do? MAR, MDR. What are they? Okay, good. Now, they are the things that the processor uses to either import this from a memory, okay, in form of instruction or data. Okay? And while that is going on, okay, some operations are going on as well. Okay? And of course, you can see your memory address register and then memory data register. Okay, so all the register that the computer needs to use are part of what you find in your CPU. Alright? And yes, you talk a little about that. You do some memory manipulations. Okay? So just have in mind about that. Just have in mind about that. You do some. Oh. Okay. And then I should not have too much.
Yes.
Are we here? What's going on here? Okay, let's do that. So now, what you are seeing here, okay, is just classification of memory based on how close they are to the CPU. Alright? So we can talk of registers, talk of cache, okay, talk of main memory, and of course talk of some other external. So this is actually based on proximity to the CPU. Okay, when we talk of location of memory, proximity to the CPU. And of course, that is part of what is considered when we are designing or building the computer system. Next slide. Yes. What? An address. Now, an address is like a name of a location of memory. Get that? Memory is divided into so many parts or segments, okay, or cells. Okay, so when you pick one of them, it has an address. It has like a name, okay? It has like a name that says, okay, so this is where it is. Alright, so that address is just like the name of a cell in memory. You get that? Yeah. Just like the name of a cell in memory. Basically, that's what it is. Alright, so every part of a memory is referenced. Alright, for you to get anything from it. When location now. This one. Okay. The previous one. No, I'm just trying to show you one of the uses of registers. Okay, registers are the ones that carry these addresses. Okay, based on instruction from your CPU. Okay, so they go social address and pick this. You get now? Okay, or deliver social data to this address. Do you get now? That's what they do. Okay, so but the major point is that every part of the memory, okay, has for an address, as a reference, alright, so that it can be uniquely identified. This is the second one. Alright, so we can also look at memory based on its capacity, okay, in terms of what size. Okay, we can look at it from that point of view. Say the natural data size of the processor. Now you must have heard 64-bit processor, 32-bit processor. What does that mean to you? The amount of what? Yes, register size. Yes. Yes. Yeah, because now you know, in the computer, we have what you call buses, okay, that actually convey all this data and instructions, okay, and those buses are made up of their own sizes, okay. Now, to some extent, we say the size of the processor bus, okay, is what constitutes whether that processor is a 32-bit, 4-bit or whatever it is, okay? It means what the capacity, the amount of data that can be processed by that CPU per time. Alright, so when you pick the 32-bit, which is just like how many bytes? Maybe 4 bytes now. Okay? It means that is what is capacity per time. Per time, now when we talk about per time, that's a different thing. Okay, but in terms of what you can process per time, it's just 4 bits or 4 bytes. When you now think 64 bits, that's 8 bytes now, okay? Now, of course, that one can do double what that 2 will do. So, if you we expect such a computer to be much faster in processing what 32-bit ordinarily would have done. Okay, so we have such things like that. So, typically, based on processor data bus bit, okay, that's what the word size is about, and the bit of an integer or an instruction. Okay, an integer is how many size? How many bytes? An integer. Huh? An integer is how many bytes? 8 bits. 8 bits. Just a byte. Just a byte. Anyway, you will discuss that further. Okay, let's move on. Another thing we can look at in terms of capacity is the addressable unit in memory. Addressable units in memory. So various of values based on the system's ability to allow us addressing and byte level. Now you will talk more about this with Dr. Zeta. You talk of addressing modes in memory. Okay? So you need to think, look at that. I will say at motherboard level, okay, this is called what? A word. Okay? But when you pick a disk, it is called what? A cluster. On your hard drive, okay, it is called a cluster. On your motherboard, it's called a word. Okay? That's in terms of the buses that actually carry this data. Okay, and then we have that here. And okay, unit of transfer. It says, the number of bits read out or written into memory per time. Okay, that's the unit of transfer. And of course, it will be internal or external. Internal is governed by what? The data bus bit, which is a word, and then external is a word, a block, which is much larger than a word. Yes, I will just discuss this and then we will stop for this part. I'll just discuss this a few months and then we stop. Now, I want you to take note of this because this is important as we discuss this. Each type of memory that you know, okay, as the way it is being assessed, there's a method, okay, that it is that is used to access it. Okay, and by that I mean RAM, which is your main memory, is not accessed the same way your cache memory is assessed. Okay? Hard disk is not accessed the same way your RAM is assessed. Alright, and that's why it's important that you take note of this, and under each one of them, note which one is for which. Okay, and of course you need to flow along that line. So we say for the sequential access method, which is very common for tape. I don't know if you have worked with tapes. Here. I don't want to go here.
Normal tape.
It's not that kind of tape now. Anyway, let's just try to apply the same logic actually. Yeah. I was actually thinking that I used to maybe in the back setting when we have stored large data for archive purpose and stuff like that. That's what I was actually interested in. It was not those tapes that you're talking about. Now I say that for this kind of access method, okay, it has to this. Now you have memory, okay, of this nature. It says you have to start from the beginning, alright, and then read through until you get to where you want or where you are looking for. Alright, so data is read based on where they are stored. Based on where they are stored. If it's stored somewhere at the middle, you have to get there in order to read that data. Okay, so a data that is stored there, ABC, okay, you can't read C until you have read what? B. You can't read B until you have read A. That's what it means. Okay? And it says access time depends on what? Location of data and the what previous location of the read-write mechanism. And of course, an example of that is your tape. An example of that is your tape. Next slide, please. Next, please. Cash works in a different way. Okay? Cash works in a if your cash is going to work that way, then there's no good service purpose at all. No good service purpose. Cash is meant for I just store this and deliver. Okay? So if you are let's have their own different way of storing things, okay? They have their own way of manipulating data. Now, the second one is direct access method. I will say this is what you find in your hard disk. Okay, this is what you find in your hard disk. Then individual blocks have their own unique address. Individual blocks have their own unique address. And access is by what? Jumping to the vicinity, okay, and then what? Performing a sequential search. Okay? Now, it doesn't go directly there, okay? It gets to where, somewhere close there, and it gets to do what? A search. Alright? And of course, note when access time also depends on the location of data and the previous location of the read-write mechanism. Now, this is the mechanism, okay, the mechanical component of your drive that reads or writes on your drive. Okay? And an example of this is your word. Next slide. Now, there's also the random access method. Alright, some are called random access method. That's still okay. But that's not the memory. Random access memory, that's RAM. Okay, but the method is what? Random access method. Okay? I'll say here, individual addresses identify what? Locations exactly. And access time is what? Consistent across all locations and is independent of previous access. So, it means it doesn't matter where it was at the last time. As soon as I say, yes, what I want, it just goes there based on the word address that you have specified. And it says what? Any location can be selected at random and directly accessed and addressed. Okay? And of course, example of that is your RAM. And lastly is your cache memory. Lastly is your cache memory. Yeah. Okay? Okay, you are trying to ask about cache memory. Okay. So, addressing information must be stored with data in a general location, data location. Okay. Now, in memory, cache access alone is an entire subtopic. Okay? Cache access alone is an entire subtopic for this one. Okay, but here just a mention of the general method that's used to access it. Alright, I will say access time here is not independent of location of previous access. Okay, and that's what makes cache memory what it is. Okay, at any point in time, you can get what you want from there. I think I let's see how it goes on Wednesday. Okay? If I'm privileged to be around, we just round up this, and then I think Dr. Adeta will be ready to take over. Yeah, but I will post this to Modu this evening. Oh no, not this evening. Tomorrow morning.